Now that we looked at using the quotient rule to find derivatives, we can actually use it to give us the derivatives of the remaining trigonometric functions that we haven't talked about. So these are the ones that aren't sine and cosine. These are the rationals: tangent, secant, cosecant, cotangent. Because they're actually fractions of sine and cosine, we can use the quotient rule along with the derivatives of sine and cosine that we already know to figure out what their derivatives are. So let's just do one example. We'll do this here in terms of sine and cosine for tangent, and then we'll just simply know that these same steps can be applied to find the other derivatives. At the end of the day, all 6 trig derivatives are something you need to memorize and not have to work through like what I'm going to show you here. I simply want to demonstrate how it's done to justify why they look the way they do and how they come about. So first off, if we consider tangent, we're going to rewrite tangent into the sine of x divided by cosine of x. Now we know the derivatives of both sine and cosine, so to figure out the derivative of tangent, we're just going to use the quotient rule to make that happen. So that means the derivative is going to be the derivative of the numerator, so the derivative of sine is going to be cosine, and then we'll multiply that times the bottom, which again is cosine. Then we subtract from that the derivative of the bottom, which is negative sine, so that makes this a plus, and then we multiply that by the numerator, sine of x, and then we divide the whole thing by the denominator here, cosine squared. So this is kind of where it works out to be. Now we can simplify this expression and use our identities to clean it up and make it look nicer. And again, the same process can be applied to the other rational trigonometric functions to find their derivatives as well. So on the top, if I have 2 cosines, well, that's going to be cosine squared. And the same is true when I multiply sine times itself. Now on the bottom, again, we'll just keep this cosine squared here. But the first thing that jumps out at me, of course, is that sine squared plus cosine squared, that's equal to 1. So we actually end up with 1 divided by cosine squared. And that's pretty cleaned up and pretty okay to use, but I think it's a lot nicer if we just use the reciprocal idea, because if you divide by cosine, that's the same thing as multiplying by secant. So the conclusion I can make is that the derivative of the tangent of x is equal to secant of x squared. Now again, we can repeat this process with the other ones to obtain their rules, and they end up looking like this. So please don't redo all that work and do all the simplifying every single time. Instead, we're going to add these 4 to the 2 we've already memorized. Okay, so our responsibility when finding derivatives is to know all 6 trigonometric ones. So the derivative of sine is cosine, and the derivative of cosine is negative sine, but in addition to that, the derivative of tangent, like we just saw, is equal to secant squared. With pretty much the same style of simplification, the derivative of cotangent, when you do the quotient rule, is negative cosecant of x squared. Now, when we do secant, again, doing this quotient rule and simplifying and putting like terms together, its derivative is the secant of x times the tangent of x, and likewise the derivative of cosecant of x is the negative cosecant of x cotangent x. These need to be memorized, and the more you practice and work with them, the easier it'll be to use them. So let's look at a couple examples. Here in our first example, we have f of x, and that's just x minus tangent x. So when you want to find the derivative of x is going to be 1 by power rule. And then we subtract from that the derivative of tangent, which we know to be the secant of x squared. So as soon as you memorize them and really get them, right in the front of your brain, it's going to be easier to just plug them right in. Now, when we look at example B here, and I want to find the derivative, we have to recognize right away that this is a product rule. Okay, we have x times secant of x. So the overall, structure is going to be a product rule, but within that, we'll be using the derivative for secant. So to do it, we find the derivative of the first term, x, which is 1, times the second, so it's 1 times the secant of x. And then, of course, we add the derivative of the secant of x, which is the secant of x times the tangent of x times the first term, which is x. Now, like we talked about before, anytime you're dividing by a single term, it's always real helpful to go ahead and break it up to avoid using the quotient rule. So I'm going to go ahead and do that. I'm going to rewrite this function as 1 divided by sine, which is the cosecant of x, and then subtract from that cosine divided by sine, which is the cotangent of x. So instead of doing the quotient rule, now I can simply use the derivative rules for these trig functions that I've memorized. So that means in this case, the derivative of f prime is going to be the derivative of cosecant of x, which is the negative cosecant of x times the cotangent of x, and that's minus the derivative of cotangent of x, which is negative, so this becomes a plus, cosecant of x squared. Now, something to keep in mind is that whenever you look at the trigonometric derivatives, having done a couple examples now, one pattern you should notice is that the derivatives, right, of the trig functions that begin with the letter C are always negative. And this is even true when it comes to the sine and cosine. Remember, the derivative of cosine, which does start with a C, is equal to negative sine x. So one way as you're trying to memorize these to keep things straight is, again, to remember any trig derivative, right, of a trig function that begins with the letter C has a negative derivative. So now that we've talked about using the derivatives, let's go back and practice our basic skills. So let's write the equation for a tangent line to the graph of secant at x equals pi over 3. So, of course, the first thing we need is the derivative. So the derivative of secant is going to be the secant of x times the tangent of x. To write the equation of a tangent line, I need my point and I need my slope. Well, the x value is going to be pi over 3. So to figure out the y value, that means I got to plug it into secant. Well, the secant of pi over 3 is the same thing as 1 divided by the cosine of pi over 3. And since the cosine of pi over 3 is 1/2, flipping that over makes it 2. To find the slope, we're going to go ahead and plug it into the derivative. So that means we'll take the secant of pi over 3, which is the 2, and then we'll multiply that times the tangent of pi over 3, which is radical 3. So that means my slope of the tangent line will be 2 radical 3. So when I put all that together in point slope form, it'll be y minus our y value 2 equals our slope times x minus our x value. So now that we've covered the basics of derivatives and some of the organizational structures like products, quotients, and things like that, now we can start talking about higher order derivatives. Now what this means is that we're finding derivatives of derivatives. Essentially, we'll do the process of differentiating multiple times. Now this can, of course, in a very general sense, provide us rates of change, but a good example is motion, right? The velocity is the rate of change of our position. But if we find the derivative of velocity, it gives us acceleration, which is the rate of change of velocity. And these derivatives can have a lot of applications that way. When you take more advanced calculus, higher order derivatives are used to create polynomial approximations that are really important. So right now, since we're learning how to find derivatives, we want to be able to find not just the first derivative by doing it one time, but the second, the third, the fourth, and so on to whatever nth derivative. So we want to be able to calculate many derivatives deep. It's a very important tool later on in calculus. Now, what I want to demonstrate is the notation to make sure you understand when you're being asked to find just that first, second, third, or whatever derivative. So the notation we're kind of getting used to, so far, as far as doing it one time, finding the first derivative looks like this. We can write y prime. That's one way we did it. We also, of course, often with function notation use f prime of x. And when we just have y equals, and a better way is using the dy over dx Leibniz notation. Now again, so far, we've always been finding these first derivatives. So that's why they've got the single primes and they look the way they do. But let's look at how this notation changes as it moves down so it can, communicate to you what you're being asked to find. So when I want to find the second derivative, we just add a prime to it. So for the first notation, it becomes y double prime or f double prime. And that again is telling us that we're trying to find the second derivative. So we have to differentiate once, and then wherever that derivative is, find the derivative of it. Now, in the Leibniz notation, it looks a little bit different. So what happens is we have a little 2 that goes up in the superscript for the d and then for the x. And that's something we'll talk a little bit more about later when we get more deeper into Leibniz notation. But for right now, that's the way it looks as far as the notation to tell you to find the second derivative. Now in the third derivative, we again add another prime. So this is y triple prime or f triple prime when we get all those up there. Here we just increase the number. So this is now d to the 3 over dx to the third. And again, that's communicating to the third derivative. But the thing is, we can't, at least on the first two styles, we can't just continually add primes, right? We don't have space for that. So instead, when we find the fourth derivative, beginning with that, we go ahead and stop using primes and start using numbers. And it's kind of similar that we do over here with the Leibniz notation. So instead of y with 4 prime marks, we put a little parentheses and we put a 4 inside of it. And that stands for the fourth derivative. Likewise, in function notation, we do the same thing. We sneak a little 4 in parentheses up there. And that's how we say the fourth derivative. Here, however, the process just continues on. So instead of having a 3 there, we'll just replace that little exponent thing with a 4. Now that once you get to that level, it just continues on. So whatever level of derivative you're finding, it just continues on and on in that way. So in general, the way we write the derivatives with a y could be with whatever value inside parentheses. In function notation, again, whatever number derivative in the parentheses there. And here, whatever that derivative will be, these little exponents on the d and the lower x on the bottom. Now, to show you some examples of this, we'll do a polynomial and a trigonometric function to talk about how, kind of what happens when you find more and more derivatives. There's certain patterns sometimes that show up. So let's start with our function here. We have a 6th degree. So I'm just going to continually find derivatives until we notice something happens. So first off, if I do what we've always done before, we'll just do the power rule, right? So this is our first derivative. So this would be 6x to the 5th minus 6x squared plus 1. And of course, the derivative of -8 goes to 0. So to find the second derivative, I'm going to take my first derivative that I just found and apply the power rule to that. So the derivative of the derivative is going to be 30x to the 4th minus 12x, and the derivative of 1 goes to 0. Doing it again is going to give me the third derivative. So I can go ahead and put that in here. So that's going to give me 120x to the 3rd minus 12. And then once I get to the fourth derivative, we're already down to a single term. And pattern I'm hoping you notice is that as I do this, now we're at 360x squared. We're slowly losing power and we're losing terms. When I get to the fifth derivative and I do yet another rate of change, now I'm at 720x. By the time I get to the sixth derivative, this is now a constant. And the first thing I want you to notice, of course, from a polynomial standpoint, is that when you have a sixth degree, by the time you get to that sixth derivative, you're already down to a constant. But what I think is the most important thing to understand is that when you go one more step and you get, in this case, to the seventh derivative, you now get to 0. And any subsequent derivative after that is going to remain 0. So the big deal I want you to notice with polynomials, right, is that as you differentiate, because you're losing power in the power rule, that you eventually get to 0, okay? That's a really helpful skill later on in more advanced calculus. But that's not true with every kind of function, okay? That's definitely true with polynomials. So just for an easy counterexample, let's look at something like sine of x. So if I find the derivative of sine of x, well, the first derivative here, y prime, is going to be cosine x. Then when I find the second derivative, the derivative of cosine will be negative sine of x. By the time I get to the third derivative, right, now it's the derivative of negative sine, which will be negative cosine x, since the negative goes along with it. And by the time now that I reach my fourth derivative, now I'm back to saying, well, what's the derivative of negative cosine? Well, that's negative sine, or just positive sine x. And what we should notice is that we've kind of gone back to where we started. So at least with this trig function, with like sines or cosines at least, we find a pattern that every time we get 4 derivatives, it takes us right back to where we started. And if I kept going, I would just continually repeat this process. Now, there are some functions that have no patterns and they just continually grow in exponents if they're negative, or they kind of bounce around and do more complicated functions, maybe if we had some different trig function. But sometimes, like I said, with polynomials, they go to 0, and with basic ones like sines and cosines, they definitely repeat.